In this module on vision, we will start by generally talking about sensation and perception and the difference between them, and then we will narrow our focus to vision itself. So our first question is, what is the difference between sensation and perception? Is perception constructive or instructive? Well, the difference between sensation and perception lies in the input versus the processing of sensory stimuli. Sensation involves the transduction of energy in the environment into electrochemical energy in the nervous system. For example, in the case of vision, we have photons that enter the eye and are absorbed by the retina, and the retina transduces that light energy into electrochemical energy. Of course, electrochemical energy is the language of the brain. Neurons use electrochemical energy to communicate. However, photons are light energy, not electrochemical energy. So in order for the brain to process light, that light first needs to be transduced into electrochemical energy, and that occurs via the retina. If you think about hearing, there's a process of sound waves coming through the air, impinging on your eardrum, and ultimately creating vibrations in the cochlea. The cochlea then has hair cells in it that are moved back and forth by the sound waves, and that mechanical motion is transduced into electrochemical energy. And if you think about olfaction, there's chemicals floating through the air. Those chemicals make contact with receptors in your nose. Those receptors transduce that chemical energy into electrochemical energy. And then, of course, we have taste and touch and so on. So sensation is the process of turning the energy from the environment into electrochemical energy. Perception is what happens after that. Perception is the process of interpreting that sensory information that has come into the body and ultimately to the brain. So is perception constructive or instructive? Well, it is clearly constructive. We say this because what you see, hear, taste, etc. is not just simply the sensory input you receive, it is a construction of the sensory input you receive. It is your brain's best guess about what must be going on in the outside world in order for you to have received the pattern of sensations that you received. If perception were instructive, then it would simply be instructed by the sensory information you get. But instead, what the brain does is make inferences about that sensory information. It actually goes beyond. It builds a story about what must have caused the pattern of light across your retina, or what must have caused the pattern of movement in the hair cells of your cochlea. Again, it is an inferential process. It goes well beyond the actual data to come up with a rich story about the world, but it is just a story. It is your brain's best guess about what's going on in the world. And sometimes your brain gets it wrong. This can be seen in examples of visual illusions like the one we see here. For this visual illusion, keep your eyes fixated on the central cross. Fixation is key here, otherwise, if you don't stay fixated, the illusion won't occur. So first off, you notice, without even staying fixated, you notice the illusion of motion. It feels as though there's a pattern or movement of a dot going around in a circle. Well, there really is no movement, as you're probably not surprised to find out. This is just the disappearance and reappearance of a dot in succession. One pink dot will disappear and then reappear, and then the next dot will disappear and reappear. But if you maintain fixation, all of these pink dots will eventually disappear to be replaced by perhaps one single pink dot. And ultimately, if you really keep your eyes fixated, then that pink dot becomes replaced by a green dot. So if you're getting the full effect of this illusion, then all the pink dots have disappeared and there's simply one green dot going around in the circle. However, this is not what's really happening. If you just move your eyes, you can see all the pink dots reappear. In this GIF image, there is no green dot. Your brain is adding that to the picture. Your brain is trying to explain the pattern of input it's getting, and the conclusion it comes up with is that there's a single green dot going around in a circle. Another illusion can be seen here. In this case, stay fixated on this woman's nose. And you're going to stay fixated for about 30 to 45 seconds. So go ahead and begin now, and I will just wait. Now, if you were able to stay fixated, then you are currently seeing a negative after image. An after image because you're seeing an image even after the image has disappeared, and negative because what was black in the image before is now white, and what was white in the image before is now black. And in fact, if your visual system is like mine, you don't just simply see the reverse black and white image, you actually see shades of gray in between as though it were a black and white photograph. This is explained by properties of the retina. The retina is already doing some perceptual processing. It's not just simply seeing what's out there, but it's adding information to the story. If your brain were instructive, not constructive, but instructive, if you just passively viewed light as it came into your eyes, then you wouldn't see these illusions. The fact that you do see the illusions tells you that your brain is trying to add information to the story. And what's so entertaining about these kind of illusions is that our eyes usually don't kind of screw up like this. Usually we're used to believing what we see, but illusions are especially and carefully designed to fool your visual system. All of this begs the question, why have a visual system that can be fooled? As we see, these visual illusions show us that the visual system can be fooled, but they are entertaining insofar as it is pretty rare for your visual system to be so wrong. But any visual system that is trying to go beyond the data and make inferences, to make hypotheses about what must be going on in the world, is going to be subject to making errors on occasion. And these errors can be of two types, type 1 versus type 2 error. Type 1 error is believing there is something there when in fact there isn't. And then type 2 error is believing there's not something there when in fact there is. And it turns out type 2 error is much more costly to survival than type 1 error. Take, for example, this image of a lion hiding in the grass. Now notice that a passive visual system would not see a lion. It would see parts of a lion head. It might see an ear or two. It would see an eye or maybe part of an eye, and a little hint of a nose, a little hint of a mouth. But it wouldn't be able to tie all of these together to come to the conclusion that that's a lion hiding in the grass. Your visual system and your perceptual system in general has evolved to be biased toward the type 1 error, to conclude that there's something there even if there isn't. So take, for example, two people, one has a passive visual system, the other has a constructive visual system. The one with the passive visual system is going to conclude, well, there's nothing there except pieces of a lion, but not a whole lion. And so there's not going to be a fear response. Whereas the person with the constructive visual system, whose visual system can complete the image even though not all of the object is visible, is going to conclude that there is a lion. the person with the constructive visual system is likely to run away, whereas the person with the passive visual system is going to stay in place, not fearing a lion because they can't see a lion. And of course, that person with the passive visual system will get eaten. Now, with regards to type 1 versus type 2 error, if you conclude there's a lion there when there really isn't, then you run away and burn a few calories that were unnecessary to burn. But that is better than making the type 2 error, concluding there's not a lion there when in fact there really is. That gets you eaten. So we have evolved to be biased toward these type 1 errors. Again, the perceptual system can't eliminate errors altogether, but what it can do is bias you to make one type of error versus the other. And it is evolutionarily more advantageous to bias toward the type 1 error than to bias toward the type 2 error. So we've all evolved to be biased to believe there's something there even if there isn't. Now this explains the visual system, but it can explain higher level systems or even higher level beliefs, such as belief in ghosts. Quite a few people believe in ghosts, and that usually happens when some phenomenon happens that can't be readily explained in purely physical terms. So for example, there's a light on in the attic and nobody's been up in the attic in months. How did that light get turned on? Or a door slowly creaks shut and there's no one around that could have done that. How did the door close? Well, our brains are biased to believe that somebody must be there closing that door or opening that door or turning on that light, even if there wasn't someone there. And so we get this kind of irresistible urge to believe that somebody must be there, but yet we've concluded there couldn't be any kind of normal person there. There's no physical body present that could have done this. I'm the only one in the house, or no one's been in the attic for months. And so our type 1 bias causes us to say, well, if it's not an ordinary human, then it must be some extraordinary human, something supernatural, like a ghost. Well, in fact, it may have just been that a slight breeze caused the door to close. Or maybe there's some faulty electrical wiring that has caused the light to turn on in the attic. But those explanations tend not to be satisfactory to us. Our brains want us to believe there's something there, because that's safer than believing there's not something there if in fact there is. We can even take this to explain the widespread belief in some sort of God or gods. It is very difficult to look at the magnificence of the universe and think that this all just happened randomly. It sure seems like there's somebody there that must have created the universe, presumably a god. So it may be that our bias toward type 1 error is fueling our beliefs in gods, our belief that there must be something there, even if maybe there's not. Okay, so let's get down to some nitty-gritty and talk about vision, and in particular, we'll start by discussing the eye. Now, we're not worried about most of the eye. We're going to focus primarily, or perhaps exclusively, on the back part of the eye, the retina. Now, light is going to come in from the outside. It's going to go through the lens, and as you probably know, a lens will actually flip the image over. So on your retina, at your top of your retina, light from the bottom of your visual field is appearing, and on the bottom of your retina, light from the top of the visual field is appearing. So for instance, if you're looking at someone, then their head is going to, the light from their head anyway, is going to fall on the bottom part of your retina, and the light from their feet is going to fall on the top part of your retina. So there's more evidence that your visual system is constructive, because you don't see the world upside down. You see it right side up. In fact, there are experiments done where goggles are used that actually have a lens that turns the image back over. So when you put these goggles on, the light from the person's head will hit the top of your retina, the light from their feet will hit the bottom of your retina. However, your visual system is accustomed to flipping the world over. And so it flips the world over and it gives you this disorienting, kind of vertigo-inducing experience that everything is upside down. However, after a few hours of wearing these goggles, your visual system will eventually say, well, this doesn't make any sense. Let's try flipping the world over. Ah, that works so much better. Well, now the curious thing is, the world is right side up when you've got these goggles on, but when you take the goggles off, the world is upside down because your brain is flipping the image over, or maybe more accurately, is not flipping the image over. Point is that now the head has gone back to being represented in the bottom part of the retina, the feet have gone back to being represented at the top part of the retina, but your visual system is accustomed to having these goggles on, so it is not flipping the image over. But after a few minutes, your visual system says, all right, something screwy here, let's just go ahead and flip the image over. Ah, okay, things work better. Eventually, it's interesting that your visual system learns to recognize these goggles. So eventually, after enough experience with these goggles, you can put the goggles on and the world doesn't turn upside down. You can take the goggles off and the world does not turn upside down. Eventually, your visual system learns to adjust for when you have the goggles on versus when you don't have the goggles on. So, your visual system is constructive even at the most basic level. Even though the image on your retina is upside down, your visual system flips that image over to make the world work better. So let's look at how the retina is constructed. In this image, we have the eyeball with the lens here at the front. Light is coming through the lens. It's going back through the vitreal fluid, the fluid that fills the eye, and then that light is going to make contact with the retina. And here we have a cross-section of the retina magnified so that we can see its structure. Now there are 5 types of cells in the retina. We have the photoreceptors, of which there are 2 subtypes, rods, which are particularly sensitive to low levels of light, and then cones, which are particularly sensitive to color. So there are photoreceptors, bipolar cells, ganglion cells, horizontal cells, and amacrine cells. We're mostly going to concern ourselves with the first 3 types, photoreceptors, bipolar, and ganglion cells, although horizontal cells may come into our story a little bit. We probably won't discuss amacrine cells, but certainly for the sake of the exam, you'll want to know that these are the 5 types of cells. Now, how are these cells laid out? Well, they're actually kind of backward from what you might expect. That is, photoreceptors are at the very back of the retina, yet photoreceptors are the ones that are absorbing the light that's coming into the eye. So I say this is backward because you would expect photoreceptors to be up here at front so that they get the photons first, and then they process that information and send it back to the other layers. But it's actually just the opposite of what you would think. The light coming in has to actually go through the ganglion cells, through the amacrine cells, through the bipolar cells, and through the horizontal cells before it gets absorbed by the first stage of the retina, the photoreceptors. Now, these ganglion, amacrine, bipolar, and horizontal cells are translucent, so the light travels through them pretty well, but it's kind of like having saran wrap in front of your eyes. Most of the light is going to come through, but some of it's going to get diffracted and distorted. And frankly, I've never heard a good evolutionary explanation for why the retina is built backward. Why have the photoreceptors, the ones that actually transduce the light energy into electrochemical energy, why have them in the back of the retina? If they're the first stage of processing, shouldn't they be up here up front? Seems like it, but that's not the way the retina is built. So the light comes in, and these photoreceptors, once the light reaches the photoreceptors, the absorption of those photons are going to be transduced into electrochemical energy. Specifically, a pigment inside of these photoreceptors is going to oxidize, or it's going to bleach. And when that oxidization happens, it causes hyperpolarization of the photoreceptors. Now, this is another aspect of how the retina functions that seems a little backward to me. I would have guessed that light coming in and being absorbed by photoreceptors would cause them to depolarize. However, it's quite the opposite. Light causes the photoreceptors to hyperpolarize. Now, this works because what the photoreceptors are trying to do is inhibit the bipolar cells. And if they inhibit the bipolar cells, then the bipolar cells are unable to excite the ganglion cells. And if the ganglion cells are not excited, then they don't fire action potentials. Now, action potentials, when they are fired, are going down the axons of these ganglion cells. Where are these axons going? These axons are bundling together and leaving the eye as the optic nerve. Here, by the way, is more or further evidence that your visual system is constructive, because where those ganglion cells are exiting the eye, there are no photoreceptors. That means there should be a blind spot in your visual field. That is, any light that is hitting where the ganglion cells are exiting, that light is not hitting photoreceptors and therefore is not getting processed. It's just being absorbed and transduced into heat energy and then dissipating. So that means that you should have kind of a black hole in your visual field, but you don't. That's because your constructive visual system has figured out that it doesn't make sense for there to be a black hole in the visual field. So what it does is it fills in that black hole with all the information that's around it. So you don't see a black hole in your visual field. Your visual system constructs an image to cover up that black hole, so to speak. So back to the photons hitting the photoreceptors. These photoreceptors are trying to inhibit the bipolar cells. And so when you're in complete darkness, these photoreceptors are fully depolarized, and therefore they're releasing maximal amounts of inhibitory neurotransmitter. That neurotransmitter is inhibiting the bipolar cells. The bipolar cells are unable to excite the ganglion cells. The ganglion cells, therefore, are unable to fire action potentials, and your brain, your visual system, perceives a lack of action potentials from the ganglion cells as the presence of darkness. So in total darkness, photoreceptors are depolarized, ganglion cells are not firing action potentials. Therefore, you see nothing in front of you. However, when light actually is turned on, the photoreceptors absorb that light. It causes the photoreceptors to hyperpolarize. Therefore, they reduce the amount of glutamate they're releasing onto the bipolar cells. Since the bipolar cells are not receiving this inhibitory glutamate, they can excite the ganglion cells. Now that the ganglion cells are excited, they can fire action potentials down their axons. Those axons are going back to the visual brain, and the visual brain says, aha, light is present. Let's look at this through the schematic illustration of the retina. So here the light is coming in, going through the ganglion cells, the amacrine cells, the horizontal and the bipolar and the horizontal cells, and that those photons are being absorbed by the photoreceptors. So what happens is light breaks down the pigment. It causes hyperpolarization of those photoreceptors, which causes a decrease in the release of inhibitory glutamate. Because you have a decrease in glutamate, these bipolar cells are allowed to depolarize. Since they're depolarizing, the bipolar cells can now release excitatory neurotransmitter onto the ganglion cells, which will depolarize those ganglion cells. Now that the ganglion cells are depolarized, they've reached excitation threshold, they will increase their firing rate. By the way, the only true neurons in the retina are these ganglion cells. Now, this is a difficult process to come to understand, but once you understand it, it's actually quite simple. So if you're finding in this lecture that you're not understanding this whole 5-step process, then make sure you're reading the textbook. Might have to read it a few times to understand this process, and you might want to check out videos on YouTube that relate to this 5-step process. Now let's talk about foveal vision. The fovea is at the center of the retina, okay? And it is the highest acuity vision part of the retina. If you notice, when you're reading a book, you hold the book right in front of you. You don't hold the book off to the side. If you held the book off to the side, the light coming in would appear on the periphery of the retina. But the periphery of the retina is not very high acuity vision. You have mostly rods out here, and rods are not good at seeing fine details. Instead, what you'll do is you'll move the book to the center of your visual field so that the light from the book is going straight back to the foveal part of your retina, where you have mostly cones, which are good at high acuity vision. And not only are they good at high acuity vision, but there's a structural feature in the fovea of the retina such that the ganglion cells, the amacrine cells, the bipolar, and the horizontal cells have all been pushed aside. So that at that one special place in the retina, light doesn't have to bounce around through all these other layers. It can go straight back to the cones without being distorted. In the periphery of the retina, it has to get through all these other layers, and that causes a reduction in the fidelity of the signal. You don't have high fidelity information coming in here. So, one reason that you have high acuity vision in the fovea is because the fovea has spread apart all these other layers, so light does not have to get through there. But there's another reason that the fovea is higher acuity vision than the periphery, and that is because in the fovea, one photoreceptor is connected to one bipolar cell, which is connected to one ganglion cell. And so you get a one-to-one mapping between photoreceptors and ganglion cells. However, in the periphery, a single photoreceptor is going, or actually let me put that differently, multiple photoreceptors are going to input to one bipolar cell, which is going to input to one ganglion cell, which is going to send its signal back to the brain. So in the fovea, any given ganglion cell is actually receiving a signal from many photoreceptors. So in the fovea, there's a one-to-one mapping between photoreceptors and ganglion cells, but in the periphery, there's a many-to-one mapping of photoreceptors to ganglion cells. So a ganglion cell that's receiving signals from many photoreceptors has to integrate all of that information together. It has to average that information. Therefore, it's not as high fidelity of a signal as you get in the fovea. Now let's look at another visual illusion, and this one's going to help us understand color processing. For this visual illusion, just stare at this bottom right corner star. Okay? And again, keeping your eyes fixated is going to be critical here. So I'll leave this displayed for about 30 seconds while you keep your eyes fixated. Do not move your eyes, otherwise the visual illusion will not work. Okay, so now you should be seeing a negative after image. Again, like the previous negative after image we saw, it's an after image because the image is there even after the image has been taken away, so it's an after image. And it's negative because the colors are the opposite of what you saw previously. The green stripes have turned to red, the black stripes have turned to white, the blue field where the stars are has turned to, the yellow field has turned to blue, and the black stars have turned to white stars. So it's a negative after image. Now let's consider color vision, and we'll talk about two theories for color vision. And it's going to turn out both theories are right, even though only the second theory is going to explain the presence of these negative after images. So the two theories of color vision are the trichromatic theory and the opponent process theory. As I said in the last slide, it's going to turn out that both of these theories are correct. This often happens in science. You'll have two competing theories, and some people will be in favor of one theory, others will be in favor of the second theory, and often it turns out, well, both theories are right, just in different circumstances. And that's the case here. Trichromatic theory is correct when we talk about cones. At the photoreceptor level of the retina, there are three basic kinds of cones, three basic color detectors, and these will create all the perceived colors we can see. As you may be familiar with, there are three primary colors, and these three primary colors, various mixtures of them can be used to create any different color. Now, there may be some disagreement out there on what the three primary colors are. If I were to ask students, often many students will say, well, the three primary colors are red, yellow, and blue. Others might argue, no, the three primary colors are red, green, and blue. And in a sense, both are correct, but they're correct under different circumstances. If you're painting, mixing pigments to come up with different colors, then the primary colors are red, yellow, and blue. However, your retina is not a painter. Your retina is not mixing pigments, even though it has pigments in it. It's not mixing pigments to make color. It's mixing light. And when you're talking about mixing light, then the way to make all the possible colors is red, green, and blue. So, even though painters use the color wheel with primary colors of red, yellow, and blue, we are using the color wheel involving the primary colors of red, green, and blue. Okay, so you have red cones, green cones, and blue cones. And what we mean by that is not, of course, that the cones themselves are colored, but rather red cones have pigments that are maximally oxidized by red light, green cones whose pigments are maximally oxidized by green light, and blue cones whose pigment is maximally oxidized by blue light. And so your perception of the various colors is dependent on the extent to which red cones are hyperpolarized, the extent to which green cones are hyperpolarized, and the extent to which blue cones are hyperpolarized. And so trichromatic theory explains very well what's happening at the level of the cones. However, by the time the information gets to the ganglion cells, trichromatic theory no longer works. At the level of the ganglion cells, it's opponent process theory which explains color vision. And at the level of the ganglion cells, we don't have red, green, and blue cells. We have red-green cells, we have yellow-blue cells, we have white-black cells. Red-green ganglion cells are active when you're seeing red light, but inhibited when you're seeing green light. Yellow-blue cells are active when you see yellow light, but inhibited when you see blue light. Now, if there are red-green ganglion cells, then there are also green-red. So green-red cells are maximally active when you're seeing green, but they're inhibited when you're seeing red. And that helps explain the negative after image we saw with the American flag. When you stared at the green stripes in that initial image for about 30 seconds, it activated your green-red cells. And those green-red cells were firing maximally. They were firing so strongly that they were starting to get fatigued, such that when we went to the next slide, which was just white, those green-red cells didn't just go back to baseline, which indicates the presence of no color. They actually dropped below baseline, which in these opponent process theory cells actually corresponds to the perception of red. So your brain thought you were seeing red when in fact there was no color being presented. Why? Because the green-red cells became so fatigued after looking at green that when you took the green away, they dropped below baseline. And when those ganglion cells drop below baseline, your visual system takes that as the presence of red. So this is one way that we can fool through visual illusions your visual system. Now let's talk about center surround receptive fields. Ganglion cells have this curious property of center surround receptive fields. Now, this stuff is a little bit difficult to understand, and so you're definitely going to want to augment your understanding by reading the textbook on this. Center surround receptive fields refer to the fact that light falling in the center of the receptive field has a different effect than light falling on the surrounding part of the receptive field. So here we see kind of a donut shape with the center of the receptive field and the surround of the receptive field. Okay? There are two types of center surround receptive fields, center on and center off ganglion cells. Center on ganglion cells are ones that fire when light appears in the center of the receptive field, but the neurons or the ganglion cells are inhibited when light hits the surrounding part of the receptive field. So let's look at this display of spikes or action potentials here. So when we have our neuron going along at baseline levels of firing rates, okay, when a light is turned on in the center of that receptive field, the ganglion cell increases its firing rate. Until the light is turned off, it goes back to the baseline level of firing. Now, if we shine light instead in the surround of the receptive field, the neuron actually gets inhibited. It has fewer spikes or action potentials. So again, when light is hitting the center of the receptive field, the ganglion cell fires vigorously. When light hits the surround part of the receptive field, the neuron goes below baseline levels of firing. So ganglion cells are just the opposite. Off ganglion cells are just the opposite. When light hits the center of the receptive field for an off cell, it turns the cell off. It goes below baseline levels of firing rate. But when light hits the surrounding part of the receptive field, it excites the ganglion cell, and the ganglion cell increases its firing rate. So this is the concept of center surround receptive fields. And one of the reasons that those are particularly important is because they give rise to a property referred to as edge detection. Edge detection is a fundamental feature of the visual system. If you think about it, edges are much more important to your survival than center of objects are. So for example, if you're going to pick up an apple to eat it, in order to grab the apple, you need detailed information about where the edges of that apple are, and so that you can accurately grab it. Information about the center of the apple is not terribly important. That's not what is helping you grab it and eat it. It's the edges that are important. So our visual system has evolved to really accentuate edges. This can be seen in part by looking at these color swatches over on the left here. If you look for each color swatch, you will notice that right where the border is, that the gray is a little bit lighter on this side of the border, and then on the opposite side of the border, the gray is a little bit darker. That is, if we look at this first patch, it's kind of a light gray, but right as you get to the border, it's an even lighter gray. Now, the next patch is a darker gray, and right at the border, it's an even darker gray. Follow that gray patch over here, and on this side, it's actually a bit lighter, and on the opposite side, it's actually a bit darker. So that's true for each one of these borders. Now, you're seeing lighter gray and darker gray, but that's not because the image is drawn that way. For each of these gray patches, they're uniformly gray across the entire patch. They're not lighter or darker at the edges. Your visual system is adding that information. It's called a contrast effect. Your visual system is enhancing the contrast. And to understand that, you need center surround receptive fields. So if we take these center surround receptive fields that are in a uniformly gray part of the color swatch, then they're receiving equal amounts of light in the center and the surround. And so consequently, they're getting excited by, if these are center-on cells, for example, they're getting excited by the light that's hitting the center of the receptive field, but they're getting inhibited by the light that's hitting the surrounding part of the receptive field. Therefore, their overall firing rate is at baseline. Not much signal is going back to the visual system from these ganglion cells. However, a ganglion cell whose receptive field falls on an edge is in a different situation. It's receiving light gray in the center of its receptive field, which is causing it to get excited. It's receiving light gray in the surround, which is causing it to inhibit. But because there's an edge there, the part of the inhibitory receptive surround receptive field is actually not as inhibitory because some of it is receiving darker light. Okay, and so the inhibition coming from this part of the surround receptive field is not as great. There's an overall greater excitation for these receptive fields because the center is completely illuminated and only a partial area of the surround receptive field is being illuminated. So there's more excitation in the center than there is inhibition in the surround. That means these ganglion cells that happen to fall on an edge are going to send stronger signals to your visual system, which is going to cause just this side of the border to appear particularly bright. Okay, so again, this is complicated stuff, and if you're not following it, you definitely want to be reading in the textbook to get this down, and you want to be searching for videos on YouTube that help explain this.